Well, hi there, everybody. I don't know if you realize it or not, but this is the last video you'll have to watch for AP Calc this year. We'll still do lessons in class live over Zoom, but this is the last pre-recorded video that I am gonna be doing with you guys. So huzzah and hooray for that. But I do have to apologize because I'm really sorry. I made a few other minor changes to the notes, and so I know you just went into your module and got an updated version, but I need you to go back into the module and get another updated version for 7.3c because otherwise you'll notice some differences when you're watching the video. So pause right now and go ahead and get that. All right, so I assume you've got that, and we're going to keep working with the washer method today, which is the method we saw using discs or discs with holes that specifically make the washer method. But what we're going to do is we're going to rotate it around things other than the x-axis. So let's start with, what if we wanted to rotate an original region? So the original region is this one down here. I'll make it green. Okay, that is the original region, which you can see partially dips below the x-axis. So we can't use the x-axis to rotate because the x-axis goes through the original region. So we're going to use a different axis. We're going to call the axis A, and we're going to rotate the region around that. So that region sort of skewers the center, and we sweep this region up and around, and it forms a series of washers that decrease in size and with the center out in the middle. So we've got a washer piece. Oops. So right here we have another washer piece that's formed kind of in the back with a center hole. So all of these washer pieces being formed as we rotate around an axis other than the x-axis. Okay, there. So hopefully you can start to visualize it. The outside really becomes solid. You know, we can't see what's going on the inside, but the inside does have a hollow center, a hollow core that goes all the way through. So let's maybe do it like this. So there's all of those center rings all the way down, and the only opening you can see then is at the very end, but you can see all the way through. All right, so we need to add some subtraction because we're moving the axis of rotation. So we call this axis of rotation alpha, and we insert an alpha as a subtraction within the radius of what we're doing. So we're going to do f of x minus alpha and g of x minus alpha quantity squared. The other thing you've got to notice is this f of x piece right here. You have to stop thinking of f of x as the top piece. So f of x is not necessarily going to be the top piece anymore because the axis of rotation has moved to be above the region. So you need to think of f of x as the function farthest from the axis of rotation, the greatest distance away. All right, the function farthest away from the axis of rotation. So let me help you see where that is. I'm going to erase all of this. Okay, if my axis of rotation is alpha, from my alpha, if I measure to each curve, so to the blue, let's keep our colors consistent. I'm going to go to the blue arrow to the blue curve and a red line to the red curve. It's pretty easy to tell which one is farther away. Okay, the blue curve is farther away from the axis of rotation than the red curve, so that would be the curve that would come first, which is the parabola in this case. So if we're setting this up, our parabola is going to be x squared minus 2x minus alpha, which is whatever the axis of rotation is set to be, parentheses squared pi. And then the g function is the one that's closer to the axis of rotation. In this case, it's simply the linear x, so x minus alpha, and that quantity squared. And then the whole thing, of course, in the dx with our bounds here, and our bounds are 0 to 3. So let's practice working one out all the way. Okay, so let's sketch it for ourselves. So we're going to go from 0 to pi halves, and the function is 2 sine x. 0 to pi halves. So 2 sine x has an amplitude of 2. And there's my pi halves. And the region, the other equation is y equals 2. So we're bounding between these two. So this is the region that we're looking at. Okay, and our axis of rotation is set to be y equals -1. So our axis of rotation is down here through quadrants 3 and 4. Okay, if we want to draw some visuals in terms of determining which is farther away, so if I go straight to that edge compared to straight to the other edge, then we can see that the linear piece is farther away from the axis of rotation. So we'll set up our volume. Our volume will go from 0 to pi halves, as indicated in the question. Parentheses, pi, parentheses. And then 2 is the function farther away from the axis of rotation, minus the axis, which is -1, that quantity squared. And then minus pi times the inner axis, which is 2 sine x, minus -1, that quantity squared dx. The most common mistakes that people make when they're setting these up are not paying attention to their parentheses, and especially when they use Math 9 on the calculator, missing out on the parentheses there. So let's clean this up. I'm going to factor the pi out, and I'll have 0 to pi halves. And what I'll be left with is 2 minus -1. That's 2 plus 1, or 3, and that is squared, so that just becomes 9. Minus, and then we've got a double negative again, and so I'll have 2 sine x plus 1, that quantity squared, and that quantity dx. You'd eventually FOIL that out, and you would simplify. Okay, our emphasis today is not going to be on the mechanics of doing those integrals. It's going to be on the setting up of the integrals and making sure we have the setup correct. So let's take another one. Although I know this looks the same, but we have a different axis of rotation. So I've got my sine x, excuse me, 2 sine x, and the line. All right, so same bounds. Okay, here's my region. And now my axis of rotation is the line y equals 2. So when I rotate this, I'm going to have a perfect reflection right above it. And then it'll be rounded. So this is not going to have any core to it. It's going to be a completely solid piece all the way rotated around this axis of rotation. Kind of reminds me a little bit maybe of a Hershey kiss in that shape. All right, so let's set up our volume for this. The bounds don't change. and pi times. Okay, now it should be pretty clear which one is farther away, because we've got our axis of rotation is the same as one of the boundary lines. So those two, of course, if they're the same, they are the closest to each other. So the one the farthest away is the 2 sine x. So I'll have 2 sine x minus the axis of rotation, which is 2 also, squared. And then minus pi times the boundary line of 2 minus the axis of rotation of 2. And then a parentheses and then a dx. So we can clean this up by taking the pi out to the front. And I'll have the quantity 2 sine x minus 2 quantity squared. And then this is going to be gone because it's a value of 0. So then we just have dx. And that's the setup for the volume when the axis of rotation moves to a different place. So suppose in a different question, the axis of rotation was a little bit higher. Suppose the axis of rotation was at y equals 3. Well, what changes about this problem? Not a whole lot. The only things that change are the value of the axis of the rotation. So this does significantly clean up here, and we would change our axis of rotation to be minus 3. And then we're going to have 2 minus 3. So that's all that changes there. We don't have a 0 this time, so that would be different. But so all that you have to worry about is the position of the axis relative to the shape and which of the boundaries of the edges of the shape are farther away from the axis of rotation or not. Just a pro tip, if you end up with a negative volume, that means you had the order wrong at the beginning. All right, so you can go back and fix that. Okay. How about 2 plus cos x and the line 1? So let's take a look at what that looks like. All right, we know that regular cos x looks like this. And then we are, with an amplitude of 1, and then we are doing 2 plus cos x. So we're going to move this up. Okay, here's my graph. So then now that's up to 3. So I think I will erase this other one. We don't need that anymore. Okay. All right, and then we need the line g of x equals 1. So that's just a horizontal line here. Okay, so we have the equation, the area bounded between these two things. Okay, so we'd like our axis to be y equals 4. Well, y equals 4 is above the region itself. So when we would rotate this, there would be a gap. What would that look like? Let's see if I can sketch that for you. All right, we would have, that would be going to the back, kind of like a drum, maybe. Maybe that would be the case, with sort of an hourglass curved out of the inside. So here's the outer edges of the rotation, but we do for sure have a core that's see-through all the way through the center. So we've got this. Okay, this interior that's completely hollow on the inside. All right, well, that's just the drawing. Let's set up our equation for volume. All right, what are the bounds here? Well, we need to know where these equations intersect each other. And we should know, because of the way the minimum of a cosine graph goes, that that's going to be at pi and negative pi. And then we'll have parentheses, pi times. Okay, well, which equation is farther away from the axis of rotation? Which one is forming the outside solid part of this equation? And that would be the line g equals 1. So I'll have 1 minus the axis of rotation, quantity squared. Now don't worry that that's going to be negative, because the square will take care of it, right? 1 minus 4 is negative 3, that square will take care of that. Minus pi times, and then of course the interior would be 2 plus cosine of x, that quantity squared, that whole thing dx. So there's a couple things we could do to clean this problem up. One, we could pull the pi out to the front. So I might do that first. And let's see, I'll put pi in front of this, which means I can get rid of my pi both on the insides. Okay, that would clean it up. I also could use symmetry in this because it is perfectly symmetric on both sides of the y-axis. So I could change my lower bound to 0 as long as I doubled my overall volume. So this could simplify to be 2 pi on the bounds 0 to pi of 9 minus the quantity 2 plus cosine of x, that quantity squared, and the whole quantity applied to the dx. So that might be a quicker, cleaner way to write that answer. Okay, well, could we rotate it around the y-axis? For sure. Here's some samples of problems that are rotated around the y-axis. This one, because it has a curve that is lower on the y-axis, it ends up with this little like dimple on the inside. I kind of love that. It looks like a little poof cushion or something that might sit in your living room. And then this one has the gap here. So when you rotate it, you're going to end up with this cylinder down the center. So you can certainly have a vertical axis of rotation which pierces the center of your shape. So how does that change what you're doing? It doesn't change a ton. It just changes the terms that you do it in. So if you're going to rotate vertically around something, everything switches to y terms. So your bounds switch to y values. Your function switches to y terms. And beta is the value of a vertical axis. If alpha is the horizontal, then beta is the vertical. So the setup of it looks very much the same. The pi times the function. Now how do you decide which function comes first? Well, again, it still has to be farthest away from the axis of rotation. And so you'll determine that based on your drawing, which is the farthest away. Okay, so for this problem, maybe I shouldn't have written that right there. Okay. All right, my bounds are going to be 0 to 4, pi times. All right, my equation is right here, but it has to be converted to y terms. And so x would be equal to the cube root of y. So I'm going to have the cube root of y minus 0, which is the axis of rotation right now. And then minus pi times. Okay, and then so I was doing my outer edge right now. Now my inside edge is the same as the y-axis. So that'll be 0 minus 0. That's pretty boring. squared the whole quantity dy. So you could significantly clean up this, this integral. Let's try setting up another one. All right, here's a parabola, x minus 2 squared. So remember that minus 2 means it's been shifted 2 to the right. And so I've got a parabola coming off of here. Okay, I also have the line x is 1. And so my area is bounded by that equation. Now it's rotated around the y-axis. So that's going to look like a little mirror image piece on the other side. And we're rotating it around. Okay, so there we go. And there's a piece in the back. So this has a cylindrical core carved out of it, but we do have a solid outside, a solid exterior with a hollow core. All right, there's my shape. Looks like the top of a volcano or something with a solid core down the middle. All right, well, let's set up, because we're rotating vertically around the y-axis, we want to set up our volume. Now we need to find our bounds in terms of the y-axis. So on the y-axis, this will go from 0 and then up to 1. So my bounds for my volume will go from 0 to 1, pi times. Okay, then I want to look at this original region, and here are the edges that I'm looking at. Okay, the parabola edge is the one that's farthest away from the axis of rotation, but it's not in y terms. So I do need to switch that into y terms. So I'm going to square root both sides, which means I have a plus or minus x minus 2. And then I add 2 to both sides. And now the question becomes, do I use the plus or the minus? And it does matter. Okay, it does for sure matter. So if you're looking at your parabola here, the parabola was shifted over. Half the parabola is on one side and half the parabola is on the other. Okay, the right side is the positive one, the left side is the negative one. Okay, you've got a plus on one side, a minus on the other. So we need to make sure that we use the minus in our equation, the minus version. So that would be minus rad y plus 2 minus the axis of rotation, which happens to be 0 for the y-axis right now. And then we square that quantity. Minus pi times. Okay, the inside was the line x equals 1, so that would be 1 minus the axis of rotation, that quantity squared, the whole thing dy. So let's clean this up. Pull the pi out to the front. That will leave me with negative rad y plus 2, that quantity squared, minus 1, the whole thing dy. And if this was a calculator active question, your Math 9 would work fine on that. If you needed to do it by hand, you'd need to FOIL and integrate each term. Okay, same original region, but we're just going to rotate it around a different axis, and this will be our last one. Okay, so our same little original region from 1 to 2, still with the equation x equals negative rad y plus 2, and the other equation x equals 1. And we're taking this and we're rotating it around the line x equals 4. So a little bit farther out on our x-axis. So here's our line of rotation. So let me extend this a little bit. So my region's going to come out here and get rotated out there. And so I'm going to have this big open cylinder with the base, a core carved out of that base. Okay, so it's a bowl, but the bowl doesn't hold anything because it's just going to go right through that open center. All right, well, let's set up our volume. Our volume is still always bounded by what the original region was, and the original region was 1 to 2. So it's not like this is going to go all the way out to 1 to 4 or 1 to 7, which would be all the way out here. It's still 1 to 2 because that's the original region. And then pi. Okay, now we want the edge that's farthest away from the axis of rotation, that's forming the outside part of this shape, which is the number 1 right now, minus the axis of rotation, which is 4. And then minus pi times, now our interior one is negative y plus 2, minus the axis of rotation, which is 4. So altogether, we'll end up with, again, 9 minus the quantity, negative rad y minus 2, quantity squared, dy. So if you have Math 9, if this is calculator active, you may just evaluate at this point. If it's not, you'll need to FOIL and integrate each term. All right, so thanks for your attention today. Hope this goes well with you. I look forward to seeing you in the morning, and we will do our very last lesson of the semester, our last new lesson, 7.3D. We'll finish it up, and then we're on the home stretch. So well done, everybody, and I'll see you in the morning.